All right, we're going to go ahead and get started now. I'd like to thank everyone who is joining us today. Welcome to today's CNCF webinar, the Event-Driven UI, Bridging the Gap. I'm Caitlin Barnard, Marketing Manager at CNCF, and I'll be helping to moderate today's webinar. I'd like to welcome today's presenter, Kevin Bader from Accenture. So just a few housekeeping items before we get started. During the webinar, you're not able to talk as an attendee, so there's a Q&A box at the bottom of your screen. Please feel free to drop any questions in there, and then we'll hold those to the end and get to as many as we have time for. The session is also being recorded and will be sent out afterwards along with a link to the presentation. So with that, I'll hand it over to Kevin to kick off today's presentation.
Thank you, Caitlin. Hi, everyone. My name is Kevin Bader. I work for Accenture Technology, where I specialize in distributed systems and event-driven architecture. 2 years ago, my interest in this type of architecture got me involved in one of our internal projects. An event-driven approach was used to solve a series of industry-specific use cases. While trying to find elegant ways to add an event-driven front-end to the microservice-based application, we've noticed that there wasn't really a good solution to do that, at least not for microservice setups. In this session, I'd like to talk about the challenges that we saw and share the open source project called Reactive Interaction Gateway that we've created to address them. First, I'm going to outline where we are right now and how we could do better. Then I'll define the vision, which basically describes where I think we should be. The challenges are the problems that we set out to solve. And after that, I will finally present our open source project as a solution to those challenges. With the expectations set, let's take a look at the as-is picture. First, the simple one. With a single backend and a single frontend, there is only one source of data, and with that, also only one source of events, which makes it pretty simple to figure out where to get the data from. In such a scenario, implementing server-side push of real-time data can be as simple as adding a WebSocket endpoint to a microservice. If that service goes down, we'd lose all client connections, but since we've lost the only server as well, this doesn't matter a lot. Now let's head over to the microservice world. Microservices are best designed around business domains and capabilities, which enables teams to largely work autonomously. We often strengthen this independence further by making microservices event-driven. Microservices publish domain events that other microservices can subscribe to, which decouples applications and lets us add downstream microservices easily. As an example, this picture shows two microservices that implement an authentication context and a customer profile context. The customer profile service deals with customer profiles, but not with login sessions, for example. Let's say the customer profile service would like to use session statistics to enrich its customer profile data. In order to gather those statistics, the service could subscribe to session-related events published by the authentication service. On the backend, this makes the microservices, as well as the implementing teams, loosely coupled. But there is still only one frontend, often maintained by a single team and meant to include data from multiple, if not all, microservices. So we asked ourselves, wouldn't it be nice if the frontend team could selectively subscribe to events the same way that microservices teams do? And this exactly is our vision. Microservices and frontends produce and consume events in the same way. This should, of course, only rely on open standards. And to keep true to loose coupling, frontend should not be aware of how events are stored on the backend. This means that if we're using Kafka partitions on the backend, for example, the frontend should neither care about Kafka, nor should it know anything about the partitioning scheme used for those topics. A naive approach would be to have each microservice maintain a long-lived connection to the frontend. But that approach has some drawbacks. Firstly, the infrastructure would have to deal with vast amounts of connections. For example, with 50,000 online users and 50 microservices, we'd have to provision not for 50,000 connections, but instead for 1.25 million connections in total. But what's even worse is that it forces microservices to maintain connection state. In turn, this means that redeploying microservices breaks front-end connections and facing the load of 50,000 connecting clients right after startup. Of course, that's doable, but it would be much better to offload that connection handling to a dedicated service instead. That service wouldn't contain any business logic, and because of this, wouldn't need to be redeployed that often. We want the microservice to not care about who consumes its event, which is kind of the whole point of event-based decoupling. Consequently, a microservice shouldn't need to publish some kind of special event for front-end consumption. Instead, any published event should be consumable by both other microservices and front-ends. We defined some goals for the front-end as well. As mentioned already, front-end should be agnostic of the way events are stored on the backend. To easily support browser-based apps, there shouldn't be any proprietary formats involved. Frontends should be enabled to publish events towards microservices. Frontends should also be enabled to control what kind of events they receive by maintaining event subscriptions themselves. Let's look at the technical challenges in detail. The first one is about scaling with the number of users and with the rate of events. The second item is about different sources of events. The third one is about an interesting problem around how to give an event-driven microservice ecosystem a classical synchronous boundary. Finally, we touch upon the topic of authorization. Let's start with scalability. In general, a typical system has way more users in total than are online at any given point in time. However, depending on the business domain, this can still mean a 5- or 6-digit number of connections to deal with. If this doesn't already call for horizontal scaling, dealing with large amounts of events certainly does. Messaging systems like Apache Kafka typically organize topics and petitions to distribute the load. A single consumer that is subscribed to all of those petitions is overloaded quickly. Given the events are already grouped into those petitions, it would be easy to let frontends subscribe to petitions directly. However, that would violate one of our goals, as frontends would need to know how the event topics are partitioned on the backend. Instead, we need to repartition events according to their event type. Because the event type is what is relevant to frontends, as that's what they ultimately subscribe to. Now a few words on event sources. Of course, not everyone is using Kafka. But while initially we've seen the need to support other message brokers as well, it seems that Kafka has become the de facto standard for implementing this type of architecture by now. You have the Confluent Kafka platform that many companies use, and additionally, each cloud provider now has an offer around Kafka as a service. For example, even though Azure Event Hubs might have a non-Kafka implementation under the hood, it still provides a Kafka-compatible interface to its clients. As a synchronous alternative to Kafka, it should also be possible to publish events using a simple HTTP call. While this appears to violate the don't publish special events goal we've defined earlier, it actually doesn't. The submitted event is still an event, and it should be processed the same way. One example where this can be helpful is publishing events while decrypting them on the fly without revealing the encryption key. Going for microservices and event-driven architecture also means embracing eventual consistency. In such a model, most interactions are asynchronous, which makes it easy to add and remove services, among other things. But the way we implement processes internally shouldn't affect our public APIs. Most third-party clients expect a traditional HTTP API that doesn't respond with "I'll do this later," but with what was requested. This requires some sort of conversion between the two paradigms, and I'll go into details on this a bit later. Last but not least, there is also the concern of authorization. Authorization is essential in this setup, as the idea is to potentially subscribe to any event, which of course includes those that contain sensitive information. At the same time, the solution should contain as little business logic as possible, meaning the authorization mechanism should be plugged into it in some way. Next, I'll talk about two candidate solutions and point out why they didn't meet our requirements. The first one is Microsoft's SignalR. This is from the official documentation and shows how to set up a real-time dashboard for IoT devices. Here's the relevant part. The authenticated clients connect to the SignalR service via WebSocket. The data sources publishes events towards the SignalR service, which then forwards them to the client. SignalR handles WebSocket connections to frontends. A big bonus is that there is a managed SignalR service on Azure that can be used in serverless functions. Microservices, so that's a plus. Microservices publish events using a remote procedure call on the front end through the SignalR hub. A microservice can target a specific user, a user group, or all users at once. Unfortunately, this is far from our idea of publishing events in a decoupled way. Frontends are agnostic of the backend setup, but they're required to use a SignalR client implementation. The protocol is open and available on GitHub, and frontends can run remote procedure calls too, but since they also need to target a specific service, they cannot publish events in a sense. Finally, as microservices target users and user groups explicitly, frontends cannot choose what to receive. Out of the box, there is no notion of event subscription. So we move on to the next candidate, which is Pushpin. Pushpin looks pretty solid, and their key ideas seem to align very well with our goals. Transparency towards clients, statelessness and share-nothing architecture to support high scalability, and a publish-subscribe model for data transmission. Let's see how this relates to our goals. I also copied a paragraph from their website here, where they say that Pushpin has no built-in support for connecting to specific queues or brokers like Kafka, but they have an example for adding a small worker program that runs alongside Pushpin that should add that capability. So Pushpin handles connections to frontends via SSE, WebSockets, or long polling. Microservices publish messages using HTTP calls against Pushpin with a special HTTP header set. This deviates from our goals of unifying the concepts of publishing an event to other microservices and publishing an event towards a frontend. Frontends are agnostic of the backend setup, as Pushpin strips the special headers sent by microservices. The protocol is simple and built on standard abstractions. Through the WebSocket connections, frontend can send back data, but again, this targets specific services and cannot be used to publish events. Finally, frontends cannot choose what to receive. Pushpin routes events according to channels that are assigned by the microservice that sends the data. Although both solutions looked promising at first, we felt that there must be a better way to do this. So we set out to create a new open source project called the Reactive Interaction Gateway. After working on it internally for a year, we've released it on the Apache 2.0 license on GitHub 2 years ago. Since then, we have used it successfully in client projects and are happy with the results so far. It is currently a CNCF landscape project. The Reactive Interaction Gateway handles long-lived server-sent events connections over HTTP2, or alternatively also WebSocket connections over HTTP1. As a fallback, support for classical HTTP long polling is in the works as well. It is designed to listen to all events that occur in the backend and quickly drop those not relevant to any frontend. There is no need to target a specific frontend. The events that can be picked up by other microservices can also be picked up by frontends. By repartitioning events according to event types and subscription constraints, the Reactive Interaction Gateway hides the backend's partitioning scheme. To the front end, there is only one source of events. The reactive interaction gateway also relies only on established web standards like SSE and WebSocket, and also on cloud events, the upcoming CNCF specification for events. Through its HTTP reverse proxy, the reactive interaction gateway allows frontends to publish events using a simple HTTP call. And because subscriptions are maintained by frontends rather than by backends, the frontend team is in control over which events they receive. Now, let's head back to the challenges that I've described earlier. The first one was about scalability. RIG is designed to be deployed in a cluster setup on Kubernetes. We're using a Kubernetes headless service for peer discovery, and RIG connects newly spawned nodes to the cluster automatically. Towards Kafka and Kinesis, they're nodes from a consumer group, which means that Kafka partitions and Kinesis shards are distributed among the nodes in the cluster. Each partition or shard is assigned to one node, and when a node fails, the partition or shard assignment is rebalanced. In the case a new node is spawned, the assignment is rebalanced too, so new nodes get their share of events eventually. Towards clients, RIG's primary channel is servers and events over HTTP2, but due to the popularity of WebSockets, we've added support for that as well. As a side note, I'd like to mention that due to the way WebSockets work, it's quite unlikely they will ever be supported over HTTP2. Plus, SSE is a very good fit for a use case like this, which is why I strongly recommend going SSE. On the right side of the slide, you can see further details on how we implement this. There are connection processes at the top and Kafka consumer processes in the bottom that are both local to a node. Then there are session processes that exist only once for each session. They can receive messages from any node. The session processes are subscribed to event filter processes. On every node, there is one filter process for each event type encountered, and the event subscriptions are replicated among them. An incoming event is dispatched to the local filter process that matches its event type. The filter process compares the event with the subscriptions. If there is a match, the event is forwarded to the respective session process and in turn to the attached frontends. The reactive interaction gateway currently supports Apache Kafka and Amazon Kinesis for consuming events. There are also HTTP endpoints that allow microservices as well as front ends to publish events using HTTP calls. Our gateway also allows us to provide a traditional API to an event-driven backend. One of our clients deals with third-party clients that strictly require a RESTful HTTP interface. Using RIG, the client is able to provide this while keeping internal processes asynchronous. Let's see how this works. When an external client or frontend sends an HTTP request to RIG, I call Reactive Interaction Gateway now RIG for short, RIG produces a message representing this request to a Kafka topic, adding a correlation ID to it. A microservice picks up the message and does some processing. When processing is complete, the microservices produce the response to another Kafka topic, retaining the correlation ID from the original request message. RIG picks up the response, finds the associated HTTP request using the correlation ID, and finalizes the still open HTTP request by sending back the response read from the Kafka topic. This also works with Kinesis shards in a similar way. Also note that RIG can, of course, also forward the HTTP request like a normal reverse proxy would. RIG supports 3 ways to tackle authorization. The simplest one is not to do authorization at all and just assume that requests have already been checked by another service. The more common one is expecting a JWT and verifying the JWT signature before accepting subscription requests. In case you never heard of JWT, it stands for JSON Web Token and is basically an authorization token that is sent along with the authorization header in the HTTP request. The most flexible authorization scheme is to specify a custom endpoint that accepts subscription requests. RIG forwards such requests to that endpoint and accepts or denies subscriptions according to the response code sent by the custom endpoint. A similar mechanism is in place for event submissions, as depicted in the diagram. Here is a summary of the license and standards we use in the project. I've mentioned all of them, so I'll go to the next slide. RIG doesn't have any external dependencies, so it's very easy to run it. Basically, it can be operated like a stateless service. All configuration options are exposed via environment variables, and the Docker image is available on Docker Hub under the Accenture Reactive Interaction Gateway repository. So I'm already at the end of my talk, basically. To conclude it, let me say that real-time UIs are state-of-the-art and the way to go for modern UX design. We believe that extending the event-driven architecture style to the frontend is a great way to implement this. I have shown various challenges that come with a pattern and ways how to address those challenges. I've introduced the Reactive Interaction Gateway, which is our implementation of those ideas. Feel free to check out the project on GitHub and please let us know what you think. Also, we're always looking for contributors. I'd like to shout out to Dominik Wagenknecht, who came up with the original idea to this. Also to Mario Mackay, who's been working with me over this, on this over the past 3 years. And to the software innovation team at Accenture for their continuing support. Thanks a lot for your attention and feel free to send me your comments on Twitter and also ask questions in the QA forum here. So thank you for your attention.
Awesome, thanks Kevin for the presentation. So as you mentioned, we have some time for questions now. Just a reminder, there is a Q&A box at the bottom of your screen, so please drop any questions in there, and we should have plenty of time to get to them. So there was one question that came in here, and it's more of a clarification back on, I believe it was slide 19, as to what exactly you meant by events on that slide, I believe. And please follow up if I have the wrong slide here.
What exactly I meant with events?
Yes.
So if a microservice would publish an event to a Kafka topic, for example, RIG would pick up that event because RIG is supposed to listen to all those Kafka topics. And then if a frontend is subscribed to that event type, it will get that event forwarded. And the event might be any business event. Like in the example I had earlier with the customer profile event, customer profile service and session service, it could be the session service could emit an event for a user logging in or that describes that a user has logged in, and an event that describes that a user has logged out, something like this. So it could really be any kind of business event that might be interesting on the front end to show or to react to. If that answers the question. Perfect,
thanks for the clarification. Another question here, is this bound to Kubernetes or can it be run outside of Kubernetes?
It can, of course, run outside of Kubernetes. You can run the Docker image standalone. Yeah, I just wanted to show that it's easy to run it on Kubernetes because since it has no external dependencies, it can just be scaled up, scaled down. You don't have to maintain a stateful state or something like this. So I just wanted to showcase this, but it does not depend in any way on Kubernetes. So we have, actually we have multiple ways to do peer discovery also. So you could also use DNS-based peer discovery, and we have 2 other ways to do this.
All right, another one here. What are the scaling limits?
We are currently conducting benchmarks on this. So far, we have been doing only a small series of benchmarks where we were operating with, I think it was 4 or 5 nodes on AWS T5X Notch, I think. But I have to, we will publish a blog post on this because we are in the process of trying to figure out what the limits actually are. But it should be pretty good because it's built on the Erlang runtime, in case you know it, which is basically built for horizontal scalability. So yeah, I don't have the numbers right now, but we're in the process of doing the benchmarks.
All right, and then how would you handle more than 6 open tabs when using SSE?
It's easy if you're using HTTP2, because HTTP2 is multiplexing individual connections over a single TCP connection. So with HTTP2, you have 2,000 streams, I think, available, half of it upstream. So you can open 1,000 SSE connections to a single host. If you use HTTP1, though, you have to be careful not to open too many of those connections. So what you would typically do then is in your front end have a single location where you would open that connection and then use the callbacks to, I don't know, if you, for example, if you use Redux, you could dispatch an event when an event comes in through SSE, and you don't have to open an SSE connection in every one of your React components, for example. That's also one of the reasons why we recommend using HTTP2 over HTTP1, because of that multiplexing, because it makes things so much easier.
Awesome. How would you filter for events for specific clients? For example, each unique client will get a topic to subscribe to.
So Rick supports, so the main way to subscribe to events is by event type. But in addition to this, subscriptions can also contain a set of constraints. And those constraints point to specific fields in an event. Now, let's say, for example, that that there are user events and the user session ID is included in the event at a specific location, so it can be extracted using a JSON pointer. And then the subscription can contain a constraint that says this session ID field has to have that value. And then you subscribe to different types of events, but only then if that session ID field has the value that is specified in the subscription. So you can use those constraints to further filter down events, not only by type, but also by value of arbitrary fields within that event.
All right, and then are there any limitations of this platform as of now?
Not that I'm aware of. I know that we have to deliver the benchmarks and the performance numbers, so I cannot really give you any specific numbers on this here. But other than that, I'm not really aware of any limitations. What I would be curious about what would really be interesting to know is whether this concept of subscriptions and constraints resonates with the community, whether this is powerful enough or already too confusing. So I would really love to get some feedback on this. Right now, for the use cases that we have used Rick in, it was sufficient. But yeah, as I said, I'd be curious to learn about new use cases.
Another one here. have you thought about event versioning between the backend services and client-side code, something like the schema file in protobuf?
So we currently don't support protobuf, but we do support Evero because it's prevalent with a Confluent platform. But so with Evero, we convert the Evero encoded event to JSON. So it kind of loses that attached schema in a way, but it's still the same fields with the same semantic. And that those fields and this data is simply forwarded by Rig. So if you upgrade or if you do a backwards or forwards compatible change to a schema, you have to do that with your clients, so with your front ends and back ends. And Rig doesn't really do a lot with that data, except if you use it in a constraint, for example. So Rig doesn't. So you don't have to update Rig in that sense, but also Rig doesn't help you with that. So if you have a change that requires all your, let's say you have a service that publishes, that used to publish an event in a specific format and a lot of frontends depend on it, and now that service completely changes that event, doesn't publish the old event anymore, but only the new format that no one can read, then your frontends will break. Rig will happily forward the events, but the frontends cannot read it. So in that sense, Rig is really an infrastructure component and doesn't interpret the event formats or the event data that you send around. So that's a completely different concern in that sense.
All right, and then does Rig align with the CNCF Cloud Event Standard?
Yes, we're working hard on supporting most of it. There is currently an open, so we are conforming with the 0.2 standard of cloud events itself, and we're also working towards support of the transport binding spec. There is currently an open pull request for the transport binding 0.2 for HTTP for the HTTP endpoints. We've also added initial support for the transport binding as we think it will turn out for Kafka, but there is no official binding for Kafka yet. So that's basically the HTTP binding adapted to Kafka and Kafka headers. Yeah, but the short answer to this is yes, we are working hard on following the spec and implementing it properly.
Okay, so this next question is a two-part question here. So is Rig fully stateless? And in theory, it could scale indefinitely. That's the first part, if that's correct. And then how does the client know which particular Rig node to connect to?
Okay, I answered the last question first. The client doesn't have to know which node to connect to. You can just put a load balancer, like here in this picture also, you can just put a load balancer in front of it. Rig will take care that events are routed internally to the connection, regardless of where the connection connects to or where the connection ends up. So that was the second question. And the first question was about whether Rig is stateless and in theory could scale indefinitely. Of course, nothing can scale indefinitely. There are, so with the default setup of the Erlang runtime, you should be able to scale up to 50 to 60 nodes. After that, you need to tune what in Erlang is called distribution. So by default, all the nodes talk to each other, and this doesn't work with more than 50 or 60 nodes, so you have to use something else there. So far, no client has had a need for this, but that would be a fun experiment. So yeah, I actually don't know how to what extent this is scalable yet, but I will find it out. And of course, Rig does have internal state because it holds connections. It has to maintain connection state. And there are also other features in Rig, like, for example, I've mentioned JWT validation. Rig also supported JWT blacklist, which means that a client that connects with a JWT that has not expired yet, but is on that blacklist, will be thrown out. That blacklist, of course, is also state, and all the state within the Rig cluster is replicated in an eventually consistent way among the cluster. This is implemented using CRDTs. So as long as one of those nodes lives, you can you can scale up again, and the nodes will rebalance and replicate the data again. So that's why I mentioned for scaling out Rig, it feels like a stateless service, because it's actually not stateless, but it only has in-memory state and is self-healing. That's why it feels like a stateless service.
And then are there examples or sample apps using this architecture on GitHub?
No, not yet, but I'd love to see some. We're only using it at client projects right now. And those projects are, of course, not public, so I cannot show anything. But please reach out to me if you have a project and you want to include Rig. I'd be more than happy to help out.
And then another question in here: how is Rig doing discovery?
Is this about peer discovery? So if you add additional.
Yeah, specifically using Zookeeper or just DNS discovery?
As I mentioned, you can have multiple ways. The default on Kubernetes is to have a headless service that where all the nodes, where you can basically retrieve the endpoints of the other nodes that are online. But let me. Yeah, I have to check the other ways. I know that we have DNS discovery, but I don't actually know whether we support Zookeeper, because we're basically using a library to do this. So it's not something we implemented ourselves. So I looked it up. We have also UDP-based discovery in case it helps. But I think that the DNS-based discovery and this Kubernetes-based discovery should be enough for most use cases.
All right, this next question, this is a long one. So if you can filter by event field value, how do you dispatch particular front-end clients to a particular node, since Kafka partitions can be partitioned totally differently? So given that events for a single front end can be on all Kafka partitions, how would you solve that?
Let me go back to a different slide to answer that. So what, if I got the question correctly, it's about that events are grouped here by partition, and that partition could be something totally different than event type. So for example, this could be partitioned by a user ID. which makes a lot of sense because, for example, Kafka only guarantees ordering within a single petition. So if you don't want a user to have her events kind of shuffled all the time, you would likely petition by user ID. And then here, because of that subscriptions, you need events grouped by event type. Now what Rig does here is it routes events to the node where the client is actually connected to. And all the nodes know of all the subscriptions. So that's what's replicated among the cluster. I have a picture on this. Oh, it was here all the time. So here I have the event filter that knows about, there is one event filter for each event type, and it knows about all the subscriptions. So it has a pointer to those session processes. So if, for example, this client here connects to the leftmost node here, but the Kafka petition where the event type that the frontend is interested in is contained is over here. So that node will actually receive the event from Kafka. Then what happens is that this node also knows about the subscriptions for the session process that is on the other node. And it will send over within the cluster the event to that node, and this node will then push down the event to the front end. So in a way, Rig is repartitioning the Kafka petitions that are attached to it.
Awesome. So we got through a lot of questions there. Do you want to just go back to that final slide you had, Kevin, so everyone has your information if they have any other questions later on? Awesome. Well, thank you again for a great presentation. Like I said, the webinar recording and slides will be online later today. And thank you to everyone who joined us today. And we look forward to seeing you at a future CNCF webinar. Thanks, everyone.
Thank you very much for having me. Bye.